Hello world, it's Siraj, and how do we build reliable machine learning systems? That's the question that we want to answer in this video. And the way we're going to answer that is by analyzing a paper that I found out of Google research called Likelihood Ratios for Out of Distribution Detection. It sounds kind of boring and lame, but don't worry, it is not. It's super cool. And in this video, I'm going to explain the work of these researchers. Let me just say my name: Jer Wren, Peter Liu, Emily Furteg, Jasper Snowick, Ryan Poplin, Mark A. DePristo, Joshua Dillon, and Balaji Lakshminarayanan. Okay, all of you guys, great work. In this video, I want to explain to you how they constructed their architecture, and then I wrote a small script that helps make this easier to help us examine the data using TF records. And then we're going to look at their code, we're going to look at the math behind this. It's going to be super cool, and if you watch this whole video at the very end, I'll either make a fool out of myself or I'll drop some fire rap beats because I'm going to freestyle about genomics at the end. So if anything else, just watch this until the end just for that. That's a treat for this, okay? So that's the topic for this video. How do we create reliable machine learning systems? And more specifically, how do we increase the reliability of our models when deployed in life or death scenarios, right? Machine learning that matters. Not about financial prediction, not about marketing, not about sales, not about supply chain, although supply chain does kind of matter, about medicine. Okay, I said this before in my last video and I'll say this again. Medicine is the most impactful, meaningful, important application of artificial intelligence. If you take nothing else from this video, have it be that, okay? Now let's keep going here. What they did was they applied ML to disease detection, and the data set they used for this was a genomics data set. Now, the specific objective of the paper was automatic bacteria identification based on genomic data. And so there are so many different types of bacteria out there, and 60 to 80% of bacteria out there have yet to be classified. That means that we don't know what their type is. We just have to try to research and figure that out. And so in the meantime, we want to automatically identify what type of bacteria a patient has so that we can give them the proper treatment, diagnosis, etc., things like that. And there are so many different types of bacteria out there, strep, salmonella, E. coli, etc. There's a lot out there. And so obviously medicine is the biggest use case for this, or at least the one that I care about the most, and that I think you should too, because it's a huge opportunity. But there's also self-driving cars as well. That's also a life or death scenario, right? If a car misclassifies a stop sign, then it's not going to stop, and then there could be an accident. And then there's a lot of theory around this called adversarial attacks, and then ways of preventing that from happening. And right, so a stop sign, it could either be 99% stop sign or 85% sports ball. That's clearly not a sports ball, but it predicted with high confidence that this was a part of the training set, but it's not. So that's really the problem here that they were trying to solve. The problem is out of distribution inputs. So really to frame this problem, there are so many different types of bacteria out there, and sometimes if we classify a given bacteria, let's say we've trained a model, it's fully trained on our bacterial data set. Let's say we've got 100 different classes of bacteria in this genomic data set from this nih.gov website, which unfortunately it's not working right now, guys, but don't worry, they've got some test data that we're going to use. We have some right here. So where was I? So we want to try and, we have this trained model, and what we want to do is we want to use this trained model to make some classifications on new types of bacteria. The problem is, if that type of bacteria, the class of it, does not exist in our training set, there is a high likelihood that our network will actually classify that bacteria as one of the types in our training set with high confidence. This is a problem. This is a huge problem. If we misclassify some bacterial strain that, in general, we could give someone the wrong diagnosis, we could eventually give them the wrong drug, and we could kill them. So this is a life or death machine learning scenario. We don't want to mess this up. So that's the problem, right? If we have some data point that is out of our data distribution, OOD, we'll call it OOD moving forward, out of distribution, how do we classify that? Or at least, how do we detect How do we automatically detect or create a machine that says to us, hey, this bacteria, it's not in your distribution, it's a new type of bacteria. How do we do that? And so that's the problem that these researchers tried to solve. And so this is actually an AI safety problem. Now, most people don't care about AI safety. Okay, there's a small subset of researchers that care about AI safety, but the sad reality is that most people don't care. I just know this from looking at the data from my YouTube channel. I'm just putting this out there because there's no money in AI safety. You know, unfortunately, that's the issue. But guess what? If you want an AI safety problem, this is an AI safety problem that actually matters to people today, as opposed to 50 years from now, some AGI taking over the world, paperclip optimizer, whatever. This is a real AI safety problem that matters today, okay? And researchers have been trying to solve this problem, and they've been showing solutions to this problem by using mostly image benchmarks. So say, for example, they'll train a model on CFAR, which is a very popular type of image data set, and then they'll say, okay, let's give it examples from ResNet, a different image set, and let's see if we can detect if that image is inside of our distribution or outside of it. But we need more real-world data sets, right? Images are, of course, very valuable, as in the case of self-driving cars, but we want something that just, life or death, patients, right? Healthcare. This is what matters. So that's the application. And before we really get into the math and the code and all that stuff, I want you to search this book called 10 Drugs, How Plants, Powders, and Pills Have Shaped the History of Medicine. Now, this is a book that is about the history of the FDA, which is, yes, it's a United States it is a U.S. Government organization, and I know a large percentage of my viewers are not inside the U.S., and I hear you, I love you, I care about you too, but this is still something that I think everyone should learn about, because the history of how regulations came about in this drug industry is just super fascinating. Like, for example, the guy who invented morphine, he tried it on himself, he found that he was in this dreamlike state, and so he called the drug Morpheus after the Greek god of dreams, and it was later renamed to morphine. I just think that's so cool, like how these drugs were discovered and the naming conventions that they use, etc. Anyway, check out this book, okay? Let's keep going. So despite neural networks achieving high accuracy on both the training, testing data, validation sets, all of that data that you have in your distribution, in practice, real data will likely contain genomes from novel classes that we haven't yet discovered, and of course are not present in the training data. And this is a huge problem in medicine. This is a very high value problem. Obviously, I'm not a physician. I've been talking to physicians out there, so shout out to Dr. Billings and others. Anyway, this is a real problem, right? So we want to solve this. So where do we begin with this? So first of all, genetics, a little bit of genetics 101, because when I close my eyes, I used to see ones and zeros, and now I see A's, C's, T's, and G's, the source code of humans, of you and me. This is our source code. We are information-based beings, and a little bit more, but we're not going to go into that right now. So DNA is the building block, it's the instruction set for all living things, right? So all cells have DNA, and DNA consists of adenine, guanine, thymine, and cytosine, A's, C's, T's, and G's. And this repeated set of chemical compounds, ACTG, GCTA, GTAC, etc., will then define what a living being will look like, what its traits are, what its intelligence, its eye color, etc., things like that. So this really matters. There are more than 500 genes that are linked to intelligence. Okay, that's a lot of genes. And also, our human brain is a result of our genetic makeup. So I think if we're trying to build AGI or more powerful AI systems, we should actually start at the DNA level and look at genomes and analyze genomes. I think there's a lot we can learn about the nature of intelligence from genetics, as opposed to looking at its product, the human brain. That's just one idea, but it's something to be thinking about here. Okay, so let's look at the data set. Unfortunately, the data set doesn't work right now, but look, in general, something to know. There's two types of cells. There's a prokaryotic cells, and then there's a eukaryotic cells. And prokaryotic cells are cells that do not have a nucleus, and they don't have organelles. And they are basically, most prokaryotic cells are bacteria. And then you have eukaryotic cells, which you and I and all animals are made up of. And eukaryotic cells do have a nucleus and they do have organelles, but we don't care about eukaryotes right now. We care about prokaryotes, which are mostly bacteria. And that's the data set that they used for this problem. And they split the data up into in-distribution classes and then out-of-distribution classes as well. And they fragmented the genomes into short sequences of 250 base pairs, which is common. And so the data format is as such. We're going to visualize it. I wrote a small script to visualize that, so I want to show you guys that after this. But before we get into the data set, we have to frame this problem mathematically, right? This is the first thing we need to do. So let's get to the whiteboard, frame it, and then we'll get back to this. So what are our variables here? So first of all, we of course have D, and D is our data set. Like D equals, we'll just put D equals data set. So that's first. And then we have our data points. So our data points are going to be XY. So XY pairs in general, those are our data points. So we'll put data points there. And so that's, okay, so we have our data points, we have our data set, and then we have our distribution. So this is what we're trying to estimate. So we'll say probability of XY is our distribution. So this is kind of just like a variable legend for us. It's a legend of what all of these variables mean, because throughout the paper, you're going to see these a lot. So we'll just have this legend up here. So that's probability of XY is our distribution. And then we have X, right? X is our input. So what is X? So we're gonna think of X as the raw input. And so we can say X equals raw input, but not just any raw input, raw where X is going to be equal to either A, C, T, or G. So X is going to be a discrete input. It's going to be a collection of these discrete values. And then we have Y. And so Y is going to be the number of distribution classes in general up to K. So K is the number of distribution classes we have. So let's just write that as well. K equals number of distribution classes. Okay, and so now that we've defined these variables, let's define what our larger problem is. So what we want to do is we want to classify this out of distribution example. So we'll say we want to find the sample XY where Y, the label, is not a part of our known classes. We want to find a data point where we don't know what the Y is. That is a novel class of bacteria. That's what we're looking for. And the way they found out how to do this is they said, okay, so we're going to say the probability of X is going to be equal to the probability of X background times the probability of X semantics. So that's really their contribution right here, is they decided to look at this input data in a much more nuanced way and say X is not just a genomic sequence. There's a background to it and there's a motif to it. So we want to separate those two. And now let's get to more about that, because this is really their major contribution. Let's get back. Okay, so now that we framed this problem, let's figure out how to actually tackle this. Like, what algorithm do we want to use? Now, when we look at their paper, they saw that there was a lot of previous work in this direction, and they wanted to do something novel, because clearly none of the methods that existed were super effective, right? Because this is still a big problem. And so when looking at the baseline methods of what to compare their architecture against, they found more than 9, right? So all sorts of different models. There's the Odin method, the Mahalanobis distance of the input method. There's classifier-based ensembles. There's binary classifiers. There's clearly a lot here. These are all 9 of them. I'm not going to go into all because there's quite a lot. But anyway, there's a lot. So what they decided to do was basically this. So before I tell you what they decided to do, let's just keep in mind that there are 2 ways we can class machine learning. There's actually a lot of different ways we can class machine learning algorithms. We can say this is a supervised algorithm, or this is a reinforcement learning algorithm, or there's a lot of ways, but I think the way that is the most useful, at least for this application, is to classify them as either discriminative or generative. So in discriminative models, we are basically finding the decision boundary between classes. And so we are estimating what is called the probability of y, the label, given x, the input. Now, generative models are very different. Generative models instead estimate x given y. So it's the opposite. And so what that means is we're going to estimate the input given the output, which is the label. So in this case, a generative model will say, don't give me the input data so I can classify it. Give me the label and I'll generate the input from the model. And once that input has been generated, you can then do all sorts of things with that, right? So you can generate images and etc. You can generate all sorts of things like that. But they said, let's use a generative model here. Now, why would they do this? So I just think the whole thought strategy they went through was very brilliant, and I want to go through that with you right here, okay? So if you think about what a genome looks like, it's literally, you can think of it as a text file just full of A's, C's, T's, and G's, just A, C, A, C, T, G, A, C, just like forever, right? That's basically a genome. Like you can put a genome into a text file, a single text file, and that basically is your source code. And so this is a sequence, right? And the sequence matters. And so what do we do when there's sequence learning, when we have a sequence learning problem? We use a variant of recurrent neural networks, because recurrent networks, I've said this in at least 50 videos. I'm not gonna go into it in detail, but recurrent networks are great for sequence learning. And the best, not the best, but one of the most popular types of recurrent networks is a long short-term memory network. And so this set of equations right here kind of describes the process, right? So first you're estimating Z, and then you're going to estimate R, and then you're going to estimate H, and then you're going to use all of that to estimate the hidden state. So basically you're saying Z is equal to is equal to the weight times the input, and then you activate that, and that's Z. And then you take Z and you use it to compute H, the bigger hidden state. If you want to learn more about recurrent nets, just search RNN Siraj or LSTM Siraj on YouTube. I've got a bunch of videos on those. But basically, they used an LSTM network to create a generative model here. And what they found was when they had two graphs. In the first graph, they estimated the log likelihood for both the in distribution and the out of distribution inputs. And as you can see, they basically looked the same. So the red is the out of distribution. Ideally, this should not look like the blue. It should be way far away from the blue because it's not in the same distribution. But it shows that the distributions are the same. Clearly, this is wrong. And this is with their LSTM network that they built and they trained on the data. So there's a lot of different numbers and metrics we can use to try to classify some genome. And a very popular one is called the GC content. And what the GC content is it's the percentage of bases in a given genome that are either G or C. Now you might be thinking, how is that relevant? Well, there's a lot of different ways that is relevant in medical literature, which honestly I'm not totally familiar with yet. But let's just, for all intents and purposes, say it's a very important metric and it points in a lot of different directions here. And it's widely used for describing the genetic composition of some organism, of some genome. And so what they found was that the GC content is what was throwing off their prediction model. So let me put that into context here. Here's what they did. Here's the full pipeline. First of all, they trained a classifier on all of their genetic data. So think of all of that genetic data in the input column, so A's, C, T's, and G's, and then the label for that type of bacteria, right? And they're trying to learn the mapping there. And so then once they've trained their classifier, they'll then train a generator as well. So they train two models. They train a classifier and they train a generator. The classifier will say, given some new bacteria, classify it. The generator will say, given this input data, given a label, so given some bacteria, generate what the ACTG, generate the genome for what that looks like. So they have two models here. They have a classifier and they have a generator. Now, once we have so in practice, in production, here's what the pipeline looks like. In production, they say, okay, here is a given bacteria, classify it. Now it's going to classify it as some label in the distribution set, right? It's going to say, hey, this is salmonella, but it's not. Let's just say it's E. coli. It's not E. coli. Let's just say it's some new bacteria that we haven't discovered yet. But it's going to wrongly classify it as salmonella. So once it's classified that as salmonella, we'll then take that label and use the generator to say, given salmonella, generate the sequence here of A's, C's, T's, and G's. So now we have two sequences in question. We have the generated sequence, and then we have the actual sequence of the novel data point. And what they found was the generated sequence looked very similar to what the actual sequence was of that novel data point, even though that shouldn't be the case, right? It's like assuming that it really is a novel bacteria, it really is an out of distribution data point, they shouldn't be similar at all. Now, what is that similarity measure that they're using here? And it's called the GC content, right? They found that these novel bacteria, even if they're a totally new class, they had similar GC contents as the bacteria in their training set. And because of that, it wrongly classified it. So what that means in this case is that we need a more nuanced solution here. We have to look at the input and we have to look at it not just in terms of this whole single input. We have to separate it into both background and semantic data. In the context of images, the background is literally the background of the image, and then I would be the semantics, so the person the object. In terms of text, you have stop words like a, the, of, and then you have the keywords like genomics. In genomics itself, you have the background content, which in this case is the GC content, which can be similar between different types of bacteria, even if it's a novel type of bacteria that's never been discovered, or a bacteria in your distribution that we know about. And then you have what are called genetic motifs. And I think that's just a beautiful word for this. Motifs in literature are the main ideas of some literature or some novel. In this case, genetic motifs allow us to predict biological function, which is exactly what we want, because the biological function of a novel type of bacteria will be very different from one of the bacteria in our training set. In terms of speech, we have background noise, and then we have the speaker. So you get the concept here of separating background from semantics, both mathematically and in terms of our model when we build it as well. So the likelihood that we estimate has to explain both semantic and background components. And only if we do that will we be able to focus on the semantics and ignore the background, the GC content. Right? So how do we do that? So they did two things here. The first is they added some noise to the input. So you could call this perturbed inputs. And then they computed this likelihood ratio. They call it the LLR, a background contrastive score. And so what happens is the whole pipeline looks like this. Given some, they've trained their classifier, they've trained their generator, right? So now, given the new input, we're going to say, classify it. Oh, salmonella. Okay, this is salmonella. Generate a new genomic sequence based on that. Okay, compare that genomic sequence to the actual genomic sequence. And because that generator was trained on perturbed inputs, it's going to be less likely to strongly classify it as inside of the training set. And because of that, we can compute the similarity between both. And then we'll have a threshold value that says if it's above this threshold, then it is out of distribution. If it's below this threshold, then it's in the distribution. And so in that way, we actually have a number, we actually have math, we have actual concrete values that help us estimate the likelihood that some given data point is inside of our distribution or outside of it. So now let's look at the code. Okay, so here we are, out of distribution detection for genomic sequences. So got some good installation instructions here. So we'll go ahead and use that. Let's use their instructions, and let's just try to run this ourselves together, okay? We're gonna run this together. So first things first, you wanna download it. So you go to Google Research, because they've put everything into one file, download zip. So I already downloaded it, so I'm not gonna download it twice. And so then you're going to CD into it, and then we're here. Now we're going to install it as they say. So we'll say virtual env, Python 3, source activate. It's going to set up all the tools, pip, wheel, all that good stuff. Okay, we've activated, and now we're going to install the requirements. But let's also look at what those requirements are. We want to know what we're installing here. We got PyYAML, which is a file format. We have scikit-learn for ML. We have NumPy for matrix operations. We have TensorFlow, of course, for machine learning. We have Absol.py. I'm not actually sure what that is. Absol.py? Okay, so it's some C++ glue, basically. C++ Python glue. Okay, okay, fine. So let's install those inputs. Okay. Nope. Okay. What do you mean you can't find it? Oh, we're inside of the file, that's why. Da-da-da-da-da. Boom. Okay, yep, got it all, great. So now, let's see. So their actual bacteria data set, it's pretty big to download, so we're gonna just use the toy data set that they already have right here in the GitHub repository. But before we actually do anything in terms of training, let's just build a small script together to visualize the data and then train the model. So in order to call that shell script, we're gonna import OS for the operating system commands. And then of course we're gonna import TensorFlow because we're gonna use its visualization tool that it has embedded in order to visualize the data that they shared with us, okay? So we're just gonna have a very small script here, it's like 10-line script. It's not a very big deal. And inside of this, we're gonna say, okay, here's the main file, your main function. And inside the main function, we're gonna go ahead and say, okay, so step one, before we even write code, let's write some comments so we know what we're even doing here. So step one is to inspect the data, or we could say it's visualize the data. And then step two is to train the model on the test data. And that's actually where we call our script. So let's start with this. So step one is to visualize the data. So how are we gonna visualize this data? So let's look at what their data set, like where it's located. So of course, they have this test data here. Okay, so it's in 3 different files. In TR stands for training, in validation, and then out of distribution validation. So okay, so it's in a TF record format. So the great thing about TensorFlow is we can actually visualize what's inside of this TF record file. It's not a CSV, it's a TF record. So how do we do that? Well, we're gonna say, so for every example inside of that TF record, we want to print it out in terminal so we can actually see what's inside of it, all right? So we'll say for every example in TF dot, now here's the function we're gonna use, Python io.tf record iterator. So the TF record iterator will literally iterate through all of those records, and then we can do whatever we want with all of those records. So I'll say, here's the name of it. So it's inside of test data before 2011 in training data in training record.tf record, right? That's the one that we just looked at. This is the one. And if we go back here, we'll say, okay, so given that, for each of those examples, let's print out tf.training example from string, so whatever it is, example, and then we'll print that out. So every example we're gonna print out. Once we've done that, we're gonna say now os.system, and this is just a terminal command that we're running from Python, run.sh. Just keep things a little clean. And that's it, very simple. Not a big deal. So let's go ahead and run this and see what it looks like. Okay, so actually first, before we even do, let's just like comment that out. Let's just see what it looks like. Python, so we'll say Python 3 script.py. Okay, so now we have printed out all of those data points inside of that TF record, and we can actually visualize it, see what it looks like. So it's basically stored in this key value format, and we have the value, which is the name. So this is a label, like the type of bacteria we have, and then we have a link to its genome right here. So that's basically it. We have the bacteria, the label, Staphylococcus aureus aureus. Man, these names are hard to pronounce. And then the actual complete genome of that data point. And so once we do that, then we can train the model. And while it trains, we're going to open up TensorBoard, and that's going to start running TensorFlow on our TensorBoard on our local host, so we can visualize this data. So we'll we'll open that up right here. And so this is basically a way for us to just visualize the data that we have. We can play around with it. We can look at it. We can examine it. We can run a bunch of algorithms for dimensionality reduction to make it easier for us to visualize. Right now it's performing TSNE, TSNE. We can perform PCA, principal component analysis. There's a lot of different algorithms we can run here. So which is cool. We can look at the data in this way. We can look at the different layers, go inside, and then do different things with them. But I just wanted to show you TensorBoard very briefly. And before I forget, let me rap about some topic, and I'm gonna start with whatever is gonna show up here on this rap topic generator. Here we go, the next one, whatever it is. Drainage, okay, here we go. I look at my drainage. I try to get my genomics to go and aim at it. I try to get my data to look at it, go down the drain, and then it's in the swamp at it. I'm trying to go back from it. I'm not some kind of rap addict. I'm trying to take my data and do something meaningful because I'm bad at it. Look, I'm gonna get good at it. And so can you, because we're not bad at it. We're trying to become the best at it and do something that matters at it. Hey, look at this documentary. It's my life. You can see everything. I'm an incubant. I'm coming up from the bottom to the top, trying to give you some service. I'm looking at these words like I'm Jervis. Look at my affiliation. I affiliate myself with data. I keep doing my practice. Rap scripts are like, blah. Okay, I'm over. It's over. It's over. Okay, yo, that was my freestyle about genomics and whatever this is. I hope you like this video. Definitely give them a shout out, give them a star on their repository. Good job, Google Research. And you guys, wizards, what I want you to do is take some time to read this paper, play around with this toy data set. As you can see, you can run it on your local machine. You don't need a huge GPU for any of this. And start thinking about out of distribution inputs and how to build reliable machine learning systems. Don't just focus on accuracy, focus on robustness, explainability, power consumption, data efficiency. These are the things that matter this year in AI research. So I hope you like this video, and I'll see you soon.